Okay, we want to go over a couple of homework questions. The homework, what you had listed is homework 5 and 6, and homework 5 is 10.7, which is on page 222 of the WHIT book. And it says, I'll just insult your intelligence and read this to you. According to a survey, the daily one-way commute of workers is about 25 minutes with a standard deviation of 13. Let's write that down. Let me make a place to write this down. All right. So what is the 25? What do we call that? And by the way, if you're using an old book, I think this is one of those problems that might be different. So if you're using anything before the 9th edition, I think the numbers are not the same. So everybody altogether averages 25. So what do we call that? That's the population mean, which we call that mu. And it said our standard deviation, and that's for again for the population, is 13. Now the question is, we've got some more information. We've got 169 workers, so we're surveying 169 people, therefore N is 169, a nice number to deal with. We're going to find out here in just a second. And we find out that there, the mean time is 22.5 minutes. So that's the mean of our sample. So X bar equals 22.5, yes. So first of all, we have to remember what we need to get with our standard error. Our standard error is calculated by the standard deviation. Standard deviation divided by the square root of n. So in our case, it's going to be 13 divided by the square root of 169, which is 13. So 13 over 13 is 1. So our standard error is 1. So the question is our mean time of 22.5 different significantly than 22? So remember that Z is equal to the mean of the sample minus the mean of the population divided by the standard error. Did I get that right? I'm shooting from the hip with memory, and I don't trust my memory. I can't even remember to turn on the microphone, as you well know. So calculating the Z is going to be X bar, which is 22.5, minus 25, oops, didn't leave myself much room there, okay, divided by 1. 22.5 minus 25 is negative 2.5, which means that's 2.5 minutes in this case below the national average. So 2.5 divided by 1 is negative 2.5. Okay, so we get a Z value of 2.5. What does that mean? To what do we compare the 2.5 to? But all work, the statement was made that that's compared to the average commute time of all workers. But that's 22.5. We already know that. We've already taken that into consideration. We're testing at the 0.05 level of significance. So you'll remember that, and the question was, let's see. The question was, we determine whether the national average describes the mean commute time. That means it's non-directional, just because is our 22.5 significantly different than 25? Since it's non-directional and we're testing at the 0.05 level, I'm going to have 2.5% on each tail. So it's a two-tailed non-directional test. Now, what are the magic borders for a two-tailed non-directional is redundant? A two-tailed test at the 0.05 level of significance. What is our magic number that gives you what the borderline is between common and rare? It's 1.96, and if you need, you may want to refer back to some previous recordings if that doesn't seem familiar real quickly, because we calculated that. And for the situation as of a two-tailed test at 0.05 level, it's always the 1.96, so plus and minus 1.96. So we got the negative 2.5. Negative 2.5, I'm trying to show much on one screen, I realize, is going to be in the lower rare region. That means that the answer is no. The Chicago commuting time does not approximate the national commuting. It is significantly less because it's in the lower tail area that's a rare occurrence. So our 22.5 is less than, significantly less than a 25-minute commute. Even though it's only 2.5 minutes different, because of the standard deviation, the size of the sample, and all that stuff that plays into this, Chicago commuting time is lower than the national average. Or in other words, to answer the question the way they ask it, does the Chicago commuting time describe the national? It does not. It's different. Sorry. Questions, thoughts, comments that make halfway sense? I will take halfway. Quarter-way sense? Nobody's waiting from home. Is this going through? Or you seeing what I'm intending to show you and kind of halfway working for you? At least follow along. I see one amen. I get seconds and okay. I've got enough okays that seems to be okay. The next homework questions were 12.6 and 12.7. And 12.6 has to do with the previous situation. And actually, I kind of worked this for you last time just as an example, but let's go ahead and do it again. You remember the question about whether the female APA association members made less than average, and I think we said yes, it did. This asks us the same question, but it asks us to do it with confidence intervals instead, or a confidence interval instead. You'll remember that we did a Z-test before, and we found out once we did the formulas that we just talked about just now, that the 82.5 was significantly less, or I'm sorry, the 80,100 was significantly less than the 82,500. So here I want a 99%. I don't remember if we tested that at the 0.05 or 0.01 level, but we're asked on this one to do to construct a 99% confidence interval. Keep in mind again that the standard error, still need to know that, standard deviation divided by the square root of n, and keep in mind that the 99% confidence interval is whatever our mean is, plus or minus. Do you may remember the magic number for a 99% confidence interval? 2.58, someone says. And again, if it doesn't occur to you where that number comes from, you can go back and talk about where we found that before. But it's 2.58 times the standard error. If I got the formula right, again, I'm shooting from the hip. I'm relying on my faulty memory. Okay, so for a 99% confidence interval. Now, our mean, our sample mean is, what was it, 80,100? And do I have enough information to construct this 99% confidence interval? It is 80,100 plus or minus 2.58 times whatever that standard error is. What's the standard error? We are told that, recall that the standard deviation is 6,000. So 6,000 divided by, and what do we say N was? 100. Yeah. So the standard error is going to be, yeah, it was exactly what you said, 600. So it's 2.58 times 600. And getting out my abacus, I find out that 2.58 times 600 is 1,548. So the 99% confidence interval is whatever 80,100 minus 1548 is, which is 78,552 up to 81,648. So there's my 99% confidence interval. Now the question was, remember that our mean population, or our mu, for everybody was 82,500. So my mean salary of female faculty members is 80,100. But again, that's, you know, it's kind of is it exactly 80,100? Probably not. That's probably not it. But that gives us a bit of a range to where it's likely to be within, and that range is our confidence interval. So the 80,100 is probably somewhere between about 78.5 and 81.5. But compare that with the 82.5. Does my confidence interval, maybe this is a good way to say it, does my confidence interval touch the population average? And the answer is no. So there's a 95% chance, or actually in this case I take it back, a 99% chance that the actual mean salary of female faculty members is no more than 81,648. So there's a pretty slim chance it's actually going to reach that 82.5. So the answer is, and to the B part, given the confidence interval, is there any evidence that the mean salary falls below? Yes, there is evidence that it probably does fall below. So the same problem worked two different ways. And I know we had a lot of questions. I've gotten questions not just in class, but also some email questions about saying that I don't understand the relation between confidence intervals and the Z-testing. We'll get into more of that. I'll show you more of that when we get into other kinds of tests, like the T-test, for example. We'll start after our in the second half of the course. But that's what 12.6 asks. Again, do you follow me okay on that? Okay, I see a thumbs up, a couple of head nods, and nobody's objecting online. There's an okay. I'll take an okay. Okay, 12.7, the last homework question, refers to a problem, an exam. I don't think we did in class. Back on page 250, it has to do with, did we do the question on the mean box, the size of candy? Sometimes I do this, sometimes I don't. I didn't do that. Okay. Okay, so the question was, are we putting the right amount of candy in the box? Because, you know, not all boxes of anything weigh the same thing exactly. There's going to be a fraction of an ounce or something one way or the other. Well, that's okay if we didn't answer that question because we can answer it here. If you go back to 251, let's go back and look at the original question. That was review question 1111. Yeah, the scenario is we're putting out what we call 2-pound boxes. And I find out that I weigh all the boxes. I find out that we've got an average of 33 ounces. Is 33 ounces, does that meet the 2-pound requirement? Yes, a little more. 16 ounces in a pound. So we're getting 33 ounces ounce boxes with a standard deviation of 0.3 ounces. That means some are a little above, some are a little below. What's the likelihood that we're falling below our 2 pound limit? We don't want to fall below 2 pounds because you get in trouble for doing that sort of thing. So I've got the population standard, and I'm reading from page 266, exercise 12.7 now. We've got the population standard deviation of 0.3, so that means that lowercase sigma equals 0.3. And I've got the sample mean weight of 33.09. That means our X bar, or our mean of the sample, is 33.09. And we've got a random sample of 36, so N equals 36. I'm not going to put all these formulas up again because they're the same couple of formulas we've been dealing with. But the question is, well, it says to construct a 95% confidence interval. So a 95% confidence interval is equal to, again, the sample mean plus or minus, now what's the magic number? We've already used it today. 1.96 times the standard error. So our standard error is going to be that standard deviation divided by the square root of, in this case, 36. So 0.3 divided by 30 divided by 0.5, is that right? Is the standard error 0.5? Sometimes okay. I was about to say, sometimes I get my decimal in the wrong place. So standard error is 0.05. Okay, yeah, that's right, because I move the decimal over a place. Okay, so our 95% confidence interval is going to be 33.09 plus and minus. Oops, that was right. Yeah, plus or minus 1.96 times 0.05. And I'll figure out what that is here in a second. 1.96 times 0.05. So it's going to be 33.09. If I could write halfway decently, which I can't anyway, but you know that. Plus or minus, I get 1.96 times 0.05 to be 3.598. I see shakes of heads. Okay. Didn't look right to me either. Had too weird of a 0.0098. It still looks funny, but is that right? Is it 0.098? Okay, now I see. No, it's okay. All right, so 33.09. First of all, minus for the lower end is 32.992. Up to, adding that on the upper end, is going to be 33. I can't do that in my head. $33.188. So if that's the 95 confidence interval, with these data, this situation, there's a 95% chance I'm putting on average between 32.99 ounces and 33.19 ounces. So again, I'm concerned that I want to make sure I'm putting at least 32 ounces in. So let me ask this way: does the closest end touch the 32 we're concerned about? And it doesn't, so it's likely to be above. So 32.99 is the lower end. We want to make sure we're above, so the lower end of that's 32.99. So even the low end is more than 32 ounces. So it looks like we're putting enough stuff in there. Now the downside is it costs you more to do that, so you want to shoot pretty close to 32. Well, I'll just put 45 ounces in them all. Well, that's not going to be very good business either. So it's good to err a little on the high side in this situation, and it may cost you a fraction of a penny per box, I guess, I don't know, than it would be to shortchange people because you can't stay in business that way. But again, you don't want to give people too much for their money in this case if it hurts business, if it's bad for that. So this is a pretty good example of where we're looking at the same kind of situations we looked at with z-test, just with confidence intervals. Any thoughts, questions, comments? So those are the homework questions. Even with the point comment was made, even at a 99% confidence interval, we're still going to be above 32. I would think so, because in this case, our standard error is so small, there's not going to be much deviation around that mean that we get. So the likelihood that we're going to be very close to the mean is much higher with such a small standard. There's not much error here. Again, we know something about error. We know how it's distributed. We know we can calculate how much it likely is. So that gives us a range, in this case an interval specifically. Let me hold on to that, and you can ask that when it comes in. All right.